All right, everyone, let's delve into the concept of invariant distributions for Markov chains in this lecture. We'll begin by considering a time homogeneous Markov chain, which we'll denote as X. This chain maps from our sample space omega to the state space script X raised to the power of Z plus, which represents discrete time steps. Accompanying this chain is a transition probability matrix P, which defines the probabilities of moving from any state in script X to any other state in script X, with these probabilities ranging from 0 to 1. Now, for a key definition, a probability distribution, let's call it PI, which is an element of the set of all probability measures on script X, denoted script M of script X, is said to be an invariant distribution for our Markov chain X if it satisfies what's known as the global balance equation. This equation is simply PI equals PI times P. Another definition that's useful here, when the initial distribution of a Markov chain is given by Nu, another element of script M of script X, then the conditional probability denoted P sub nu, mapping from the sigma algebra script F to the closed interval 0.1, is defined as P sub nu of A equals the sum over all X in script X of Nu of X times P sub X of A for all events A in script F. P sub X of A here is the probability of event A occurring given the process started in state X. For a Markov chain X mapping from omega to script X raised to Z plus, we will denote the distribution of the random variable Xn, the state of the chain at time n, by nu sub n, which is an element of script M of script X for all non-negative integers n. That is, Nu sub n of X is defined as the probability under the initial distribution nu naught P sub nu naught that Xn equals X for all states X in script X. Just a quick reminder, we can observe that nu sub n of X, the probability of being in state X at time n, is equal to the sum over all states Z in script X of Nu naught of Z times the Z, the xth entry of the n step transition matrix P raised to the power n. Let's go over some important facts about the invariant distribution P. Firstly, the global balance equation Pi equals PIP is fundamentally a matrix equation. What this means is that it represents a collection of equations, one for each state in our state space. Specifically for each state Y in script X, we have Pi sub Y equals the sum over all X in script X of Pi sub X times P sub XY. Note that the size of this collection is the cardinality of script X. Secondly, the invariant distribution P is a left eigenvector of the stochastic matrix P, and it corresponds to the largest eigenvalue, which is 1. It's also worth noting that the all ones vector is the right eigenvector for this same stochastic matrix P, also corresponding to the eigenvalue 1. Thirdly, by applying the Chapman-Kolmogorov equation, if we start with an initial probability vector Pi, then Pi remains P times P raised to the n for any natural number n. This directly implies that if the initial distribution nu naught is Pi, then the distribution at any future time n, nu sub n, will also be pi for all non-negative integers n. Lastly, if a process starts with the invariant distribution pi, then this process is stationary. A consequence of this is that its finite dimensional distributions are shift invariant. For instance, for any non-negative integers k and n, and any sequence of states x0, x1, all the way to xn in script x, the probability under PIP sub pi of the sequence x0 equals x0 through n equals xn is the same as the probability p sub pi of x k equals x0 through x k plus n equals xn. This probability is given by p sub x0 times p sub x0 x 1 times dot 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 times p sub xn minus 1 xn. Here are a couple more reminders regarding the invariant distribution pi. For an irreducible Markov chain, if pi sub x is greater than 0 for at least one state x in script x, then it turns out that the entire invariant vector pi must be positive. To see why, we need to show that pi sub y is greater than 0 for all states y in script x. Let y be any state in script x. Due to the irreducibility of the Markov chain, we know there exists some non-negative integer m such that the m-step transition probability from x to y p sub xy superscript m is greater than 0. Furthermore, since pi equals pip raised to the m, it follows that pi sub y is greater than or equal to p sub x times sub xy superscript m. Since both pi sub x and p sub xy superscript m are positive, their product is positive, so pi sub y is greater than 0. Also, it's important to note that any scaled version of pi will also satisfy the global balance equation. Therefore, for any invariant vector alpha, which is a vector in R, raised to script x with non-negative components of a positive recurrent transition matrix P, the sum of its components, which is the L1 norm of alpha norm alpha sub 1, must be finite. This allows us to normalize alpha to get an invariant probability measure pi by setting p equal to alpha divided by its L1 norm. Now we come to a very important theorem, an irreducible Markov chain characterized by its transition probability matrix P mapping from script x cross script x to closed interval 0.1 is positive recurrent if and only if there exists a unique invariant probability measure pi, an element of script m of script x, that satisfies the global balance equation pi equals pip, and for which pi sub x equals 1 over mu sub xx, the reciprocal of the mean recurrence time to state x, which is greater than 0 for all x in script x. Let's begin the proof. We have an irreducible Markov chain x from omega to script x raised to z plus with transition matrix P. We'll first aim to show that if x is positive recurrent, then a positive invariant distribution pi exists and is unique. Then we'll show the converse, that the existence of such a unique positive invariant distribution pi implies the positive recurrence of x. So for the first implication, let our Markov chain X start in an initial state X not equals X, we'll recall that n sub y of n represents the number of visits to state y in script X within the first n steps of the chain, and is defined as the sum from k equals 1 to n of the indicator function that xk equals y. It's straightforward to see that the sum over all y in script X of n sub y of n is simply n for every natural number n. Let h sub x denote the first recurrence time to state x, which is tau x superscript set x comma 1. Then we know that n sub x of h sub x equals 1. The first return means exactly one visit to x at time h sub x within the h sub x interval if we are counting visits up to hx, and also the sum over all y in script x of n sub y of h sub x equals h sub x itself. Let's now focus on proving the existence part. We'll define a vector v with components in here raised to script x, where each component v sub y is defined as the expectation starting from state x expectation sub x of n sub y of h sub x for every state y in script x. Observe that v sub y must be greater than or equal to 0 for each state y. In particular, v sub x equals 1. The sum of all components, sum over y in script x of v sub y equals the expectation sub x of h sub x, which is the mean recurrence time mu sub xx. Since we are assuming positive recurrence, mu sub xx is finite. Our goal now is to demonstrate that this vector v satisfies the global balance equation v equals vp. To achieve this, let's first define lambda sub xy superscript n as the probability starting from xp sub x that xn equals y and n is less than or equal to h sub x. This is defined for all natural numbers n and all states x, y in script x. We can observe immediately that lambda sub xy superscript 1 is just the one-step transition probability p sub xy for each y in script x. Next, by applying the monotone convergence theorem, we can write v sub y, which is expectation sub x of n sub I of h sub x, as expectation sub x of the sum over n in natural numbers of the indicator function that xn equals y and n is less than or equal to h sub x. This can be rewritten as the sum over n in natural numbers of the probability p sub x that xn equals y and n is less than or equal to h sub x. This sum is precisely the sum over n in natural numbers of lambda sub xy superscript n. For n greater than or equal to 2, we can partition the event xn equals y and n is less than or equal to h sub x based on the state at time n minus 1. We sum over all states z in script x excluding x. Using countable additivity and the definition of conditional probability, we get lambda sub xy superscript n equals the sum over z not equal to x of the probability of xn equals y given xn minus 1 equals z, n is less than or equal to h sub x and x not equals x, all multiplied by the probability P sub x of xn minus 1 equals z, and n is less than or equal to h sub x.
Since h sub x, the first return time to x, is adapted to the natural filtration script f bullet of the Markov chain x, the event n is less than or equal to h sub x and x not equals x is equivalent to x not equals x intersected with the complement of h sub x is greater than n minus 1. This event is in the sigma algebra script f sub n minus 1.
Combining this with the Markov property of x and the fact that the event xn minus 1 equals z and n is less than or equal to h sub x is the same as xn minus 1 equals z and n minus 1 is less than or equal to h sub x. Since if n minus 1 greater than hx, then n cannot be lesser than or equal to h unless x return to x at n minus 1, which is excluded as z, equals x. We obtain the following expression: lambda sub xy superscript n equals the sum over z not equal to x of the probability of xn equals y given xn minus 1 equals z multiplied by the probability p sub x of xn minus 1 equals z and n minus 1 is less than or equal to h sub x. This simplifies to the sum over z not equal to x of lambda sub xz superscript n minus 1 times p sub y. Now, substituting this expression for lambda sub xy superscript n back into our formula for v sub y, which was the sum over n in natural numbers of lambda sub xy superscript n from equation star, let's say, and recalling that v sub x equals 1, we get v sub y equals sub xy plus the sum for n greater than or equal to 2 of the sum over z not equal to x of lambda sub xz superscript n minus 1 times p sub z. This can be rewritten as v sub x times p sub xy plus the sum over z not equal to x of v sub z times p sub z. This is precisely the sum over all x in script x of v sub x times p sub xy. So v satisfies v equals vp. Since v has a finite sum which is mu sub xx, it follows that p defined as v divided by the sum over all x in script x of v sub x is an invariant distribution for the Markov chain x with transition matrix P. In addition, we have pi sub x equals v sub x divided by the sum over y in script x of v sub y. This is 1 divided by mu sub x x, which is greater than 0 because the chain is positive recurrent. Now, for the uniqueness part of the proof, next we need to show that this pi is a unique invariant measure independent of the initial state x chosen to define v. This will also imply that p sub y equals 1 over mu sub yy, which is greater than 0 for all y in script x. For uniqueness, we observe from the Chapman-Kolmogorov equations and the invariance property of P equals Pi implies Pi Pnk equals Pi, that Pi equals 1 over n times Pi times the sum of p plus p squared plus dot 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 plus p to the n. Hence, for each component y, pi sub y equals the sum over x in script x of pi sub x times 1 over n times the sum from k equals 1 to n of p sub xy superscript k, taking the limit as n approaches infinity on both sides, and we can exchange the limit and summation on the right hand side. This is justified by the bounded convergence theorem, as pi is summable and the Cicero sums are bounded by 1. We obtain pi sub y equals the sum over x in script x of pi sub x times 1 over mu sub yy. Since the sum of pi sub x over all x is 1, this simplifies to pi sub y equals 1 over mu sub y, which is greater than 0 for all y in script x. This shows uniqueness and the form of pi. Now for the converse part of the proof, let pi be the unique positive invariant distribution of the Markov chain X, such that pi sub y equals 1 over mu sub y, which is strictly positive for all states y in script x. The fact that mu sub y is finite, since piy is positive for all y in an irreducible chain, means all states are positive recurrent. Thus, it follows that the Markov chain X is positive recurrent. As a corollary, an irreducible Markov chain on a finite state space script X always has a unique positive stationary distribution P. This is because in a finite state space, an irreducible chain must be positive recurrent. Let's introduce a term. An irreducible aperiodic and positive recurrent Markov chain is called ergodic. Here are some additional remarks concerning the stationary distribution P. For a Markov chain that has multiple positive recurrent communicating classes, say script C1 up to script CM, one can find the positive equilibrium distribution for each individual class. This distribution can then be extended to the entire state space script X by assigning 0 probability to states outside that class. Let's denote this by pi sub k for class K, where k ranges from 1 to m. It is straightforward to check that any convex combination of these, say pi equals the sum from k equals 1 to m of alpha k times pi k, will also satisfy the global balance equation pi equals pip. Here, alpha k must be non-negative for each k from 1 to m, and the sum of all alpha k must equal 1. Consequently, a Markov chain with multiple positive recurrent classes possesses a convex set of invariant probability measures. The individual invariant distributions pik corresponding to each positive recurrent class k form the extreme points of this convex set. Let's consider a couple more reminders. Suppose we start our positive recurrent Markov chain at a specific state. So mu of 0 is E sub x, meaning the initial state x naught is x. Then we know that pi sub y, which is 1 over mu sub y, is equal to the limit as n approaches infinity of 1 over n times the sum from k equals 1 to n of p sub xy superscript k. This is also the limit as n tends to infinity of 1 over n times the expectation starting from x expectation sub x of n sub y of n. In essence, pi sub y represents the limiting average fraction of time the chain spends in state y. Furthermore, if a positive recurrent Markov chain is also aperiodic, then the limiting probability of being in a state y is simply its invariant probability. That is, p sub y equals the limit as n approaches infinity of p sub xy superscript n. Now for another important theorem. For an ergodic Markov chain X which has an invariant distribution pi, and if mu of n is the distribution at the nth step, then the limit as n approaches infinity of mu of n is equal to pi, and this convergence happens in the total variation distance. Let's outline the proof. Consider two independent time homogeneous Markov chains x and y, both mapping from omega to script x raised to z plus, and both governed by the same transition matrix P. We'll assume that the initial state of Markov chain x is x not equals x, while Markov chain y starts with the invariant distribution pi. Consequently, y is a stationary process, whereas x, starting from a fixed state, generally is not. In particular, mu sub y of n, which is the probability starting at xp sub x, that xn equals y, is p sub xy superscript n. And the probability under pi p sub pi that yn equals y is simply p sub y. Now let tau be the infimum of the set of non-negative integers n where xn equals yn. This tau is the first time the two Markov chains meet, and it's known as the coupling time. Continuing with the proof. First, we need to establish that this coupling time tau is almost surely finite. To do this, we can define a new Markov chain on the product state space script x cross script x. Its transition probability matrix, let's call it Q, is such that Q of x v yz equals p sub xy times p sub wz for every pair of states xw and yz in script x cross script x. The n-step transition probabilities for this coupled Markov chain are then given by q superscript n of x pow yz, which is p superscript n sub xy times p superscript n sub dguz. Now for ergodicity of this product chain, since the original Markov chain X with transition matrix P is irreducible and aperiodic, we know from a previous lemma on aperiodicity that for each set of states x, y, w, z in script x, there exists some not in z plus such that q superscript n of xw yz, which equals p superscript n sub xy times p superscript n sub wz, is greater than 0 for all n greater than or equal to n naught. This ensures that the new product Markov chain is also irreducible and aperiodic. Continuing the proof, let's consider the invariant distribution for this product chain. It's easy to check that theta of xw equals pi sub x times pi surge c sub u serves as the invariant distribution. This is because theta of xw is greater than 0 for each pair xw in script x cross script x. Also the sum over all x and v in script x of theta of xw is 1. And for each pair yz in script x cross script x, we have the sum over x there in script x of theta of xw times q of xw. yz equals the sum over x in script x of p sub xp sub xy times the sum over do in script x of pi sub w p sub wz. This product is p sub y times p sub z, which is theta of yz, confirming invariance. Regarding recurrence of the product chain, this implies that our product Markov chain is positive recurrent. Consequently, each state of the form x in script x cross script x, where both components are the same, is reachable with probability 1 from any initial state yw in script x cross script x. In particular, this means that the coupling time tau, which is the first time the product chain hits a state in the diagonal set x in script x, is almost surely finite. Let's continue with the proof. For the second part, we need to show that from the coupling time tau onwards, the evolution of the two Markov chains x and y is identical in distribution. That is, for each state y in script x and any non-negative integer n, the probability starting from x sub tau p sub x tau, that xn equals y given n is greater than or equal to tau, is the same as the probability starting from y sub tau p sub y tau, that yn equals y given n is greater than or equal to tau. This follows from the strong Markov property applied to the joint process xn yn for n in z plus, where tau is a stopping time for this joint process, satisfying x tau equals y tau, and noting that both marginal processes x and y have the identical transition matrix P. Now for the limit for any state y in script x, we can write the absolute difference between p sub xy superscript n and pi sub y as the absolute difference between the probability p sub x that xn equals y and n is less than tau minus the probability p sub pi that yn equals y and n is less than tau. This difference is bounded above by 2 times the probability under the joint initial distribution delta x and pip sub delta x pi that tau is greater than n. Since the coupling time tau is almost surely finite for each initial state pair, the sum over n in natural numbers of p sub delta x pi that tau equals n is 1. Therefore, the tail sum probability p sub delta x pi that tau is greater than n must go to 0 as n becomes large. This establishes the convergence in total variation distance. Now, how do we compute the invariant distribution? When the state space script x is finite, one can find the left eigenvector of the probability transition matrix P corresponding to its largest eigenvalue, which is 1. This eigenvector, when normalized, gives the invariant distribution that satisfies the global balance equation Pi equals Pp. Let's define probability flux. Consider a time homogeneous positive recurrent Markov chain x from omega to script x raised to z plus with probability transition matrix P and invariant distribution Pi in script m of script x for any two disjoint sets A and B, which are subsets of script x. The probability flux from the set of nodes A to the set of nodes B is defined as phi of AB, which equals the sum over x in A of the sum over y in B of pi sub x times p sub xy. As a quick reminder, the probability flux from a single node x to a single node y is denoted by phi of xy, and it's simply pi sub x times p sub xy. Let's define a cut. For a time homogeneous Markov chain X with transition matrix P represented as a weighted transition graph G equals script X E W, where E are edges and W are weights. A cut is defined as a partition of the nodes into two sets, script X1, script X2. We have a lemma stating that probability flux balances across cuts. Let's prove this. A cut for the state space script X is given by a partition script X1, script X2. We need to show that phi of script X1, script X2 equals phi of script X2, script X1. To see this, we can observe that by exchanging the order of summations justified by the monotone convergence theorem, assuming non-negative terms, and then relabeling the running variables x and y, we can write the probability flux phi of script x1, 1, script x2 as follows. The sum over y in script x1 of pi sub y times the sum over x naught in script x1 of p sub yx. This is equal to the sum over y in script x1 of pi sub y times 1 minus the sum over x in script x1 of p sub yx. Expanding this, we get the sum over y in script x1 of pi sub y minus the sum over x in script x1 of the sum over y in script x1 of pi sub y times sub yx. Next, we replace sum over y in script x1 of pi y pyx by pix minus sum over y naught in script x1 of pi y pyx. The first and second terms cancel out, leaving us with the sum over y naught in script x1 py times sum over x in script x1 of p yx. Hence the result. The core idea is that the net flow into a set must equal the net flow out of it in steady state. As a corollary to this flux balance for any state y in script x, we have p sub y times 1 minus p sub y equals p sub I times the sum over x not equal to y of p sub x. This in turn is equal to the sum over x not equal to y of pi sub x times p sub xy. This simply follows from applying the probability flux balancing principle across the cut defined by the set containing only y and the set of all other states set y complement. This wraps up our discussion on invariant distributions and their properties.